I'd like to switch gears a little bit and talk about the effects of alcohol on the developing brain. So as we're thinking about, this pattern of CNS deficits, however we quantify it, 2 areas of deficit or 3 areas, 1 standard deviation below the mean, 2 standard deviations below the mean. I think it's important for us to know from a neuroscience standpoint, what does alcohol do to the developing brain? Why is alcohol a teratogen? Why are we seeing the deficits that we're seeing? And so when we think about the effects of alcohol exposure on the developing fetus, the reason it is so teratogenic is because alcohol, or a metabolite of alcohol, readily crosses the blood-brain barrier. So basically what you have is the mother drinks alcohol, the alcohol crosses the placenta, enters fetal circulation, becomes converted into a fatty acid ester, and those fatty acid esters cross the blood-brain barrier and acts as a neurotoxin to the developing brain. And the effects on the developing fetus are determined by dose, duration, and timing. How much did the mother drink? How long did the mother drink? And when did the mother drink? And so what you will see is the effects on the developing brain, the effects on the face are very much dependent on that sense of timing. And so when we think about the period of embryogenesis, so when we think about fetal development being 40 weeks, we will notice that a lot of times there can be alcohol consumption that takes place before a woman even knows she's pregnant. And I think that's really important. So if we have time, I'll reflect with you guys how I start the dialogue with a mother in whom I'm suspecting prenatal alcohol exposure. Because if a child is with their biological mother, I think we must operate from the premise that a woman did not drink to intentionally harm her child. And I think that's really, really important. And so as we're developing this dialogue with families, we must come from the presumption that there was not a spirit of malfeasance. There was not a spirit of, I am doing this to intentionally harm my baby. And so very often a woman is imbibing alcohol before she knows she's pregnant. And so what we see is that early in embryogenesis, so 1 to 2 weeks, 3, 4, 5, 6, 7, 8 weeks, that's when you have the CNS system that's developing. That's when you have these active periods of brain development. What you're also noticing is that early in these first, 6, 8 weeks of pregnancy is when you have the eyes, the teeth, and the palate that are forming. So when you are looking for facial features, so basically the eye buds start laterally, like kind of where the ears are, and then they migrate interiorly. So it's the migration of the neural crest cells, and that happens early in pregnancy. These philtral ridges, the morphology of the lip and philtrum, all of that happens, again, through this migration of the neural crest cells, and that happens very early in pregnancy, really in the first 8 weeks of gestation. So alcohol consumption in those first 8, 12 weeks, really the first 8 weeks, is what accounts for those facial features. So if a mother is drinking beyond 8 weeks of pregnancy, we're not going to see those facial features. But what you'll notice is that central nervous system, that brain development, continues to develop throughout pregnancy. So from that moment of conception all the way to the moment of birth, that brain is continuing to organize, and those neural crest cells, those neurons are migrating, and those synapses are forming throughout pregnancy. So even if you're not having facial features because of the timing, you're still having potential effects on brain development. So that's why the safe take-home message is that there's no safe time to drink while pregnant. And I think we saw someone holding one of those signs out saying that really we don't have a sense of, is there a safe amount to drink during pregnancy? And so we say there's no safe amount and there's no safe time to drink. So just, so don't do it. It's sort of the message we want to give. And so when we think about, evidence from a mouse model of what does alcohol do to the developing brain, I'd like for us to notice that on the left there's the control, so that's basically a mouse that was not alcohol exposed. And then on the right, yeah, you're right, is a mouse of the alcohol that a mouse who was alcohol exposed, and we'll see several different patterns of deficit, which I think we might recognize in children who have full FAS. So this is day of life 17 that I think is actually fairly well into their gestation. So this is like the second trimester. These alcohol-exposed mice have microcephaly, so small head circumference. We'll notice that they have a small nose, and if you'll notice the eyes are fairly wide spaced, so basically that's sort of our equivalent of small palpebral fissures. They have that elongated philtrum, which we would see as sort of a 4 or a 5. We also notice that they are missing their olfactory bulb, so that there are structural deficits. We see a fusion of the cerebellar hemisphere, so we see these midline defects, so we see these structural differences. And then, and when we look at the human models, we will notice that there are really probably about 5 areas of brain, 5 areas of neurocognitive function that seem to be particularly vulnerable to the effects of alcohol. And those include, oops, let's go back one. That includes the cerebellum, so areas that are involved in bimanual coordination, the basal ganglia, which is, again, the motor center of the brain that's responsible for motor function, the hippocampus, which is the part of the brain that's responsible for consolidation of new memory and working memory, the corpus callosum, which is a sort of the area of crosstalk between the right and left cerebellar hemispheres, and then the frontal lobe, which is the part of the brain that's really, especially our prefrontal cortex, which is responsible for executive function, working memory, planning, organization, higher order language processing. So when we think about the functional deficits that we're seeing in children who are alcohol exposed, we can sort of drill down and say from a neurochemical, from a neuroanatomical standpoint, these are the areas that have been known to be affected in prenatal alcohol exposure. So it's not surprising to us that structure predicts function. So that these structural deficits and structural vulnerabilities can give us a clue into what some of the functional deficits are that we'll see. So I'm just going to go sort of briefly into some of these different structural areas that are affected in prenatal alcohol exposure. So the corpus callosum is the part of the brain that connects the right and left hemispheres. When we have children who are prenatally alcohol exposed, you can have agenesis of the corpus callosum. So basically this connection is actually missing. Or you can have basically hypoplasia or displacement. So on the upper picture, you see that the normal corpus callosum is indicated in red. I don't know how well you can see that in the back. And the child who has the alcohol exposed is in orange. And what you'll see is, compared to the normal, that corpus callosum is actually displaced, that there is a structural difference in that connection between the left and side of the hemispheres of the brain. And that structural difference has associated neuropsychological deficits, which can include decreased bimanual coordination. So they have difficulty with sort of coordinating right and left sides of their brain, which is why some interventions have suggested that juggling is a really good intervention for children who have been prenatally alcohol exposed, because it facilitates or is meant to develop that sense of bimanual coordination, which is often affected. These kids often have impaired verbal learning abilities because of connections between the corpus callosum and the language centers of the brain. So they have deficits in their verbal learning, and then they have impaired executive and psychosocial function because there are connections from the corpus callosum to the prefrontal cortex. So again, that executive function is impaired. When we think about alcohol on the cerebellum, so the cerebellum is basically what is known as like the baby brain. It's the brain below the brain. It is an important part of the brain that is really a big sort of connection center, really important for motor function, really important for posture and balance, coordination, and attention. From the cerebellum, there are all of these neural connections to other parts of the brain. And so these connections to the prefrontal cortex, to the basal ganglia, these connections sort of between the left and right hemispheres can be affected. And children who have been prenatally alcohol exposed have smaller volumes of the cerebellum. So their cerebella are smaller. And that results in deficits in balance, bimanual coordination, attention, and again, verbal and learning memory. The other part of the brain that's often affected in children with prenatal alcohol exposure is the basal ganglia. The basal ganglia is the motor center of the brain, and it's important in motor abilities and in cognitive function, including executive function, because of connections between the basal ganglia and the prefrontal cortex. Children who have been prenatally alcohol exposed can have smaller volumes of the basal ganglia, and that results in certain functional deficits, so lots of motor deficits, so difficulties in sort of coordination and balance, as well as because of the connections to the frontal lobe, these kids have deficits in executive function and attention, difficulty with response inhibition. So one of the things that we do diagnostically is we'll do something called a go, no-go test, and it's basically the Connors performance test that is looking at inhibition. So you see a word that says blue, but it's written in red letters, and so you have to say not the word but the color that it's written, and so in which it's written, and so it requires a response inhibition. And so these kids have lots of difficulty with response inhibition. They have difficulty shifting from one task to another. They have difficulty saying blue when it's written in red, and difficulty with spatial memory, and deficits in higher cognitive function. And so one of the deficits we talked about is difficulty consolidating working memory. The hippocampus is also an area that is affected in children who have been prenatally alcohol exposed. And as we said, the hippocampus is important for consolidation of new memories, consolidation of new learning. So if I tell you something and I teach you something, that gets ingrained in your hippocampus, and so the next time you see it, it's familiar and you don't have to relearn it. So these kids who have who are prenatally alcohol exposed have often decreased volumes of the hippocampi. It seems to affect the left more than the right. We're not sure why. But as a result, they have deficits in their spatial memory and deficits in other memory functions. From a functional standpoint, these kids often have to learn the same thing over and over again. It can be really frustrating for teachers. It can be really frustrating for parents. And so the sense of having, working with them to help them consolidate new memory when that is a part of their brain that is vulnerable becomes a challenge. When we think about alcohol's effects on the developing brain, we look at their cortical development. These children have often deficits in their cognitive function, and again, we talked about their executive function. They have decreased white matter volumes and deficits and abnormalities in their white matter tracts, which are often seen when we do DTI studies, so diffuse or tensor imaging studies, which is a special, often a research tool to look at these white matter tracts. These children will demonstrate deficits in cognition, motor function, attention, and executive function. And again, I think what you'll notice is this pattern of neurocognitive deficits that emerges when a child has had heavy prenatal alcohol exposure. And it's really in their executive function, in their working memory, in their planning, their organization, and in their response to others. You know, they're not getting in trouble because they have small eyes, smooth philtrum, and a thin upper lip. They're not getting in trouble because they are developmentally delayed and they're clumsy. They're getting into trouble because they make really poor decisions. And again, it's really related to that executive function capacity. So we also know that from a neurotransmitter status, there seem to be certain specific neural pathways that are involved in FASD that reflect what the other comorbid conditions are that are often seen. So we know that the dopamine pathways and the serotonin pathways are very much involved in children with FASD. So the dopamine systems, the systems in blue, are responsible for reward and motivation, for pleasure, such as euphoria. These are involved in motor functioning, and compulsion and perseveration. So these children who have sort of impairment in their dopamine systems often have vulnerabilities in attention regulation, ADHD, impulse control. They want what they want when they want it, and they can't delay gratification. And so a patient that I saw in clinic had, in FAS clinic, had slightly lower cognitive skills. She lived out on a farm, and 2 o'clock in the morning, she had this idea that she wanted to go for a horseback ride. And so she proceeded to climb out of her second-story window from her bedroom, jump out, go to the barn, unleash the horse, and go for a ride kind of, around the neighborhood. And then I guess, I don't know why horses don't like to be woken up at 2 o'clock in the morning, but the horse threw her. And so she has all of these bruises and abrasions, and then, puts the horse back and goes back to bed. And then her parents see her in the morning, and she's like covered in dirt, and she's all scratched up. And they're like, well, what happened? Well, and she says, it's like, I want what I want when I want it. And so she had this idea, didn't really have the executive function to say, is this a good idea? What are the consequences? What are the consequences for my actions? Is this wise? Would this be prudent? And then that sense of, okay, that ability to delay gratification. Can I wait till the morning to go horseback riding when my mom helps me? Nope, I want what I want when I want it. So that sense of, that sense of inability to delay gratification, that difficulty with impulse control, which is very much dopamine mediated, is a reason that these kids can get into trouble. And so we often see that some variant of ADHD is often present in these kids with who've been prenatally alcohol exposed. Conversely, the serotonin pathways are also affected in children with FAS and alcohol exposure. So the serotonin pathway is really responsible for mood, memory processing, sleep, and cognition. And when we see these kids, because serotonin is very much a part of sort of sleep regulation, a lot of these kids who have been prenatally alcohol exposed have deficits in their in sleep. These kids are poor sleepers, they are restless sleepers, they have difficulty falling asleep, staying asleep, consolidating sleep. These kids also can have sort of mood deficits. So the serotonin pathway is very much implicated in depression. So often depressive symptoms and depression can be comorbid in children who have a fetal alcohol spectrum disorder. So to summarize, there are multiple brain regions that are affected by prenatal alcohol exposure, and structure predicts function. And so we see that the corpus callosum is often affected, and what we see clinically is that these kids have deficits in their bimanual coordination and their verbal learning. We see that the frontal lobe is affected, and so because of those structural deficits, we can see these kids having differences in their executive function. We know that the cerebellum is affected, and so from those structural deficits, we see deficits in bimanual coordination and balance. We know the basal ganglia is affected, leading to deficits and vulnerabilities in their motor control, and the hippocampus is affected, resulting in deficits and vulnerabilities in their working memory. And so when we think about the neurodevelopmental deficits of FAS, and again, we've seen this slide, we see that it's very, very complex, and it's not one size fits all, that these kids can present with cognitive problems, motor problems, social skills problems, visual motor problems, language problems, sensory deficits, attention behavior problems, memory deficits, executive function deficits. And again, it becomes really important as we're thinking about this wide presentation, really this broad net of how these kids can present to us. It requires that we have a very broad understanding of how we assess these kids. So it's not enough to just do an IQ test. It's not enough to just look at how they're sleeping. We really have to look at all of these different domains of function that we know are potentially impaired. And so what this requires from a systems perspective are a multidisciplinary team, or people with lots of different strengths in terms of assessing these different domains that are potentially affected. And we said that these are the symptoms that are seen in school-age children. When you're working with younger children, it's a completely different system, a very different way of presenting, because infants and toddlers don't have working memory, they don't have executive function, they have emerging developmental skills, and so what we see is a very different pattern of deficits. And so we have to be really attuned to the developmental emergence of these symptoms. And I think that's what's really tricky with some of these diagnostic classification systems, and I think that's the strength of the Canadian system, is that for children under 6, they only require 2 areas of deficit. instead of 3. Because if we're looking at 3 areas of deficit, 2 standard deviations, 1.5 to 2 standard deviations below the mean, that's a pretty high bar for a really little person. And so then we run the risk of saying, oh, you don't meet criteria, so, good luck, vaya con Dios. And so I think as a system, we need to be really thoughtful about how we are staying connected with these children and families who may not meet diagnostic criteria at 18 months, but may meet it at 5 or may meet it at 8. And so thinking about it from a systems point of view, do we develop a system where we assess them at one point in time and say, sorry, you don't meet criteria, good luck and we wish you a great life? Or do we create a more flexible approach where we think about these children and say, okay, you don't meet criteria at this point in time, but we know you've had the exposure, and we know that the vulnerabilities can emerge at any point along the lifespan, and so we want to create some flexibility where there is a chance to be reassessed, that we create a system where there is a chance to be reassessed over the lifespan because the deficits can emerge differentially over a lifespan. And so, the challenge, I think, and we alluded to this, of making this diagnosis in infancy and toddlerhood is that sometimes it's really hard to ascertain these facial features. So, try to measure the eyes of a 20-month-old, good luck. So, good luck. And in the absence, and so then we're faced with this idea of okay, well, there was alcohol exposure. We can't really assess the facial features because this child is so uncooperative. And so if they have one thing, they've got the lip, but not the philtrum, and you can't measure the eyes, then you're just okay, well, do they have it, do they not, And so then the other thing is, in the little guys, if we're using the criteria of CNS impairment and we're looking for, developmental delay, behavioral dysregulation, there are not very many areas of neurocognitive function that are well defined in little guys. So if we're looking for 3 areas of deficit, 1.5 to 2 standard deviations below the mean, that's a pretty high bar for a little one to meet. I mean, that child has to be pretty significantly developmentally delayed to meet that criteria. And so a lot of times the little ones who meet the diagnostic criteria are the ones who have microcephaly, like Madison. So, Mackenzie. So that little girl met criteria because she is microcephalic, not because of her developmental delay. She just had mild gross motor delay. If she did not have microcephaly, she would not have met, criteria. She wouldn't have even met partial FAS, even though she had the full face. And so that's what's really tricky. So as we're thinking about a system of care, can we be flexible and say, gosh, these are kids who have, who have alcohol exposure but don't meet the criteria. And so can we say, at risk for partial FAS, at risk for alcohol-related neurodevelopmental disorder, and can we give them services and provide interventions even though they don't meet really the strict diagnostic criteria? And so, these significant CNS deficits may often be hard to demonstrate in young kids. So when we think about diagnostically, the take-home message is that if a young child demonstrates a history consistent with prenatal alcohol exposure, we want to provide intervention anyway, even if they don't meet diagnostic criteria. And my recommendation would be, can we have a flexible system that says you don't meet criteria, but let's see you back if learning and behavior concerns arise in the future, because we know that there's a developmental emergence to these symptoms, and if a child does not meet criteria at 18 months, at 3 years, they may meet criteria in the future. So we have to have a system that's flexible to see these kids.